So welcome today to Researcher's Desk Lunchtime Seminar. It's a great pleasure to have with us Senior Lecturer Glenn Bark from Luleå University. Glenn is going to be talking with us about carbon capture and storage today. Glenn's joining us from a snowbound Luleå. That means there might be interruptions during the time if there's internet issues. And if that happens, I just ask everyone to wait there until Glenn's able to reconnect. Glenn, thank you so much for joining us for Researcher's Desk today. I'm going to turn my own camera off, but I'm going to be here and you just give me a shout if anything is not working. Welcome to Researcher's Desk.
Thank you very much. Okay, so I will have a talk about, I will share my screen to start with, right? So that you can see something as well. Now I hope you see it.
That all looks great, Glenn.
Yeah, good, thanks. So carbon capture and storage is what I'm going to talk about today. And my background is in ore geology, which seems a bit to the side maybe to carbon capture and storage. But in the past, the research that I've done has been on gold ore deposits, basically, to understand how these deposits are formed in the crust of the earth long time ago, basically. But over the past maybe 10 years, I've sort of slowly but surely transitioned a little bit away from ore geology and then into storage of carbon dioxide in the subsurface, in the bedrock, basically. And this is a transition where I've sort of gone from gold to carbon. So I changed the element, basically. And the transition that I've done maybe for two reasons. And these are my reasons then. These are my two kids. This is Svante and Oscar. And this is a picture then taken a few years ago now. Today they are 13 and 16 instead. And in this particular picture, I asked them both to sort of look really cool. And they are two persons, two ways of looking really cool in this picture here. But the thing that I want to talk about basically is something that happened then. This is 4 years ago. By the time Svante, he was 9 years old at the time. And we were sitting at the kitchen table and we were like talking about his future, what he wanted to do, what he wanted to become, and so on. And then all of a sudden, he explained to me that I think that I will live to be 25. And then obviously I immediately reacted thinking that 25, that's nothing. I mean, what are you thinking now? And then he explained the reason for this to me, saying by the time I'm 25, the ocean will be full of trash and plastic and stuff. And then it's that thing about the climate. And then my jaw just dropped to the floor and I didn't really know how to respond. I mean, as a parent, you immediately feel that you want to comfort him. You want to say that there will be no problem at all. We will fix this and you can go about living your life beautifully as ever. And at the same time, in the back of my head, I know that this is not really the case. We're in a bunch of problems as it is right now. So this feeling that I had from this conversation is something that has sort of stayed with me and acts as a reminder of some sort from time to time in the reason why I've sort of done this transition into more climate-related research and the activities that comes with that, basically. So this is a little bit about me and the reason why I'm sitting here today talking about CCS, or carbon capture and storage then. And then it's that thing about the climate, to quote Svante then. And we've all seen, the graphs. We've seen the graphs showing the concentration of CO2 in the atmosphere, the amount of CO2 that we emit every year. But instead of these graphs, I want us to start with reflecting on some numbers, basically. 40 gigaton and 40 billion tons is obviously the amount of CO2 that we emit to the atmosphere every year. And then during this seminar, which will take about an hour, roughly, as it does, during that time, 4.5 million tons of CO2 will have been emitted to the atmosphere. And then to this particular slide that I'm showing you now, this smoke coming out of this chimney, like a minute or so, this is 75,000 tons of CO2 into the atmosphere during this time. So, and just to relate that to something, 1 metric ton of CO2 has the volume basically of a small house like this. So it's the equivalent of 75,000 houses like that. So we should reflect on how many houses do you have in your neighborhood, in the town or the city that you live. 75,000 houses is quite a lot. And this is 1 minute's emissions to the atmosphere. So then we have that as some sort of backdrop, and then we can add some new numbers to this and something else then to reflect on. And obviously we recognize the 420 ppm, that's the CO2 concentration in the atmosphere. But I want to take you to this type of environment. And this is something that, at least in academia and a bunch of other jobs, that a situation that we are familiar with. We find ourselves in conference room, in meetings. There are lots of people. We sit hour after hour, and eventually the air gets sort of really thick, and it's warm and humid, and you feel a need to open the window to let some fresh air in. And then the concentration of CO2 in that room is about 1,000 ppm. And that 1,000 ppm is the start when we have cognitive effects on this, saying that we will have slight headaches, we will be poorer at decision making, we will not be as smart when it comes to problem solving and issues like that. So we open the window and we let the fresh air in, and then we can get a boost again and keep going. And then we move forward to the year 2100, basically. And then depending on scenario, the CO2 concentration in the atmosphere is projected to be anything between 400 and 950 ppm. And 950, then we are fairly close to 1,000 ppm. So by the year 2100 will not affect us here listening today, but our kids and their kids, they sitting in a conference room and sort of really warm and humid air, and they feel a need to open the window, and they open it, and there is no fresh air, basically. We will have the same concentration of CO2 anyway in the atmosphere. So this is a little bit to sort of set the baseline for what we're doing, or what we're going to talk about today. We are very good at emitting stuff, of which CO2 is one. Then IPCC for one, or the International Energy Agency, they lift the technical sort of solutions, the stuff that will solve everything. And 2 of these then carbon dioxide removal technologies, which they're called, is afforestation and reforestation, simply to plant trees where there used to be trees and to plant trees where there did not used to be trees in the past. So sort of biomass, increasing biomass. And then we have BECCS, which is to use biomass for energy and then connect it to carbon capture and storage. And also then from the IPCC that this is complementary to major reductions or cuts in the CO2 emissions as we move forward. So today we will focus on this BECCS, or the CCS technology then. And CCS in this seminar, CCS as such is very much connected to fossil fuel power plants. But the CCS technology is basically a standalone technology. It doesn't matter where the CO2 comes from, what's the origin or the source of the CO2. It works the same, basically. So whenever I say CCS, it's sort of in a general sense here, not connected to the fossil fuel power plants or the fossil fuel industry of sort. So CCS then, we have an industry, they have some sort of process, they make a product. In this case, it's something blue that they ship from this factory, and they sell it, and they make a bunch of money of that. And in this process, they will have emissions, obviously, of which CO2 will be one. So the idea behind carbon capture and storage then is to then implement some sort of filter in the chimney before the flue gas here, before it's emitted. So let the flue gas pass through some sort of filter, and then to capture the CO2 in that sense. And when the CO2 is captured, it will be able to transport it to somewhere in the subsurface, in the bedrock, where it can be stored permanently then for this. And then to add the bio to the bio CCS, or the BECCS basically, is the use of biomass to power this industry, the process that they have then. So, and then BECCS would be then considered a negative emissions technology, as we are taking CO2 from the atmosphere through the process and then capturing it and sending it underground, basically. So we're taking CO2 out of the atmospheric system here. So a negative emissions technology. So very short about this. So the capturing part then, if we are at an industry or a point emitter, an industry flue gas, it's a chimney basically, where there's a bunch of smoke coming out. Then the typical CO2 concentration, it varies a lot, but a typical concentration would be something between 10 and maybe 20% CO2 in those flue gases. And then there are two themes or two different technologies to use this. They can be in solution or they can be a physical membrane, basically. The picture here shows a solution, and sort of the gold standard today is to use amines. Amine spiked water, basically, different proportions of this, to let the flue gas then pass through this water. And in this case, in the picture that I'm showing here, we have an example where we use enzymes, for instance. We're working together, us here at LTU, with a group in biochemical process engineering. They're sort of the experts in the capturing part, and we are, as geologists, then connected to the storage part later on. But in this water then, there is spiked with enzymes, which means that the CO2 will be able, the enzyme will trip the CO2 into bicarbonates very quickly in this solution here. And then the rest of the flue gas, then potentially without the CO2, will be able to leave the system and will then be emitted to the atmosphere, the rest of it, as water vapor and so on. And in this sense, we have then captured the CO2 in this solution. Then we can choose what we want to do with this solution, then going for permanent storage, for instance. Then instead of having a point emitter, there is something called then direct air capture, or DAC, which is where we capture CO2 directly from the atmosphere. We have no point source for this. This means that this technology can be at any location, basically. And the picture here shows the Climeworks. That's a Swiss company, but acting in Iceland, that started this plant 2 years ago now. This is a small plant. They capture 4,000 tons of CO2 per year, which is pretty much nothing, basically. So if we were to look at one regular Swedish paper mill, we would need the equivalence to balance the emissions that comes from this paper mill. We would need about 200 of these plants, of these DAC plants, to balance it out. But the technology as such is simply that to pump air, and then obviously at a much lower concentration of CO2, we're at 420 ppm, through some sort of membrane again. And when this membrane is saturated, is sort of full of carbon dioxide, then this membrane will be heated to release the CO2, and then the CO2 can be diverted into a pipeline and then transported for storage somewhere. And as soon as the CO2 has been captured, then there is a decision on what's the way to go with the storage, basically. Is it to be stored offshore or onshore? Those are the sort of the two main decisions in this. And if we start with going offshore, which is the type of storage that is discussed mostly, I would say 95% in media or in science as well. So then we are at the ocean floor. There is a pipeline on the ocean floor. Basically, the captured CO2 is transported in this pipeline to a pumping station. And then the CO2 is pumped down about 2,000 or 3,000 meters below the ocean floor. So pretty deep here. But the main thing here is that we need what is this black thing in the subsurface here, which is called a cap rock. We need some part of the bedrock here needs to be very dense enough not to allow CO2 to migrate through it. Otherwise, the CO2 will escape back into the ocean and then eventually into the atmosphere again. And this is a type of storage that is being developed strongly in Norway, the Norwegian continental shelf, as it is now. And it has been used already since the 90s for enhanced oil recovery then. So we can see here, these are numbers from, this is a paper from 21, but we can see that the majority of these storage facilities is where they use the CO2 for enhanced oil recovery. Basically, if you pump CO2 down into the oil reservoir, the viscosity of the oil will be lower, so it's easier to pump out more oil from the oil trap, basically. But then injecting CO2 is a technology that the oil companies then are familiar with since at least the 90s in Norway. Yeah. So it's a sort of an established technique in that sense. Then they're also working presently, and mainly from the university in Oslo, looking at storage where they don't have a cap rock. They don't have this dense layer. This opens up more areas in their continental shelf that potentially can be used for storage then. This means that there is no cap rock, and they use a method which they called residual trapping, which means basically that they pump down the CO2 a couple of thousand meters and then simply emit it at depth here and let the CO2 slowly migrate upwards through the bedrock again. And then in these different pore spaces that are these are then sedimentary rocks. We can see this as consolidated sand, basically. There will be a lot of pore spaces in these rocks. And the CO2 will slowly migrate up towards the ocean floor in this sense. And the idea then is that more and more of the CO2 will be trapped as residuals in these pores, so that optimum no CO2 will be migrating back into the ocean, or very little of the CO2 will be found back into the ocean. And then they model that from the depth that they inject the CO2 until it eventually potentially reaches the ocean floor again. This will take several hundred years in the research that they're doing now. And this is then from the University of Oslo mainly. So these are two types of offshore storage, of which the first one is the sort of 95% of the discussion about the storage of CO2. So the business model, then, everything is a business model these days around storage. They are very active from the Norwegian side, Norwegian companies, in projects called the Northern Lights and Gassnova, basically the Norwegian state. Is very active in connecting to different industries along the coast of Sweden, for instance, where each industry will apply some sort of capturing device. So they will capture the CO2 and then ship the CO2 by ship, going to an interim storage in Gothenburg, which is planned and is soon about to be built or start building the construction. And then 1 or 2 times a week, a boat will go from Gothenburg up to Bergen, and then it will be pumped down into this pipeline and down in the project that is called Northern Lights. And the potential for Northern Lights, they plan to have a capacity which is 1.5 million tons of CO2 per year that they can inject into the subsurface. And just as out of sort of curiosity, there is a power plant in Stockholm Exergi. They plan to capture 0.8 million tons CO2 from their plant alone, which is then half of the storage capacity of the Northern Lights. So you understand that the capacity is not enough, and this will be sort of the key message basically to this whole talk. But I will come back to this very much a little bit later on. But then we will leave Norway and we will move to Iceland. And we will visit a place called Carbfix. And in Iceland, we will have, this is what's in the news every day. They are expecting a volcanic eruption in the southwestern part underneath Grindavik, a small town, which have been evacuated now, but where they expect this type of sort of fairly calm volcanic eruption. So you have magma coming up, pouring out into the terrain as a lava flow, and then this lava will eventually find its way down towards the ocean and consolidate and lithify along the way like this. And if we move a little bit closer, it will look something like this, which is like a moon-like landscape. The yellow stuff here is sulfur dioxide coming out of the lava flow here. But the sort of the neat thing, or the connection basically to CCS here, is that these rocks are very reactive when it comes to carbon dioxide. And this is what we will talk about here, because this is then onshore. Now we're on land. This is Iceland, the Carbfix project. This is a volcanic rock, a basaltic volcanic rock that they use with a process, or basically which are geochemical reactions, but we can call it a process, which is called mineral carbonation. Basically, they form solid minerals from the CO2 that they capture. And this is a fairly young technique, but it's up and running since a few years. They have been injecting CO2 since almost 10 years now in this site, in the Carbfix project here. And what they do basically with this is that they have a geothermal power plant, which is supporting Reykjavik with energy. And in this power plant, they have a CO2, which is called a scrubber. They are letting the flue gas from this power plant pass through a water, sort of a shower of water, basically. And then they pump this water to a pumping station, which is the sort of diamond-like or igloo-shaped construction in the middle. And then this fluid, then water together with carbon dioxide, is pumped down to anything between 5 and about 800 meters in the bedrock then. And then the temperature, this is Iceland, so I mean, you saw the magmatic nature of Iceland. The temperatures are fairly high. It's anything between 50 and 250 degrees at 800 meters, 250 degrees in these places. But what is happening when the CO2 dissolved in water then? This is like picture it like a Coca-Cola with no taste, basically, or a Ramlösa or something like that. So when the CO2 dissolved in the water comes down into the bedrock like this, it will react with the bedrock, and calcium ions will be released from the bedrock, and then the calcium will react with the carbon dioxide in this fluid, forming what we calcium carbonates, which we would call calcite in geology then. This is in the left-hand picture. This you can see the basaltic rock, which is the sort of the grayish, blackish rock here. And then the white things, which is the carbonate minerals precipitated then from the captured CO2 in this fluid. And these reactions are geologically super fast. This happens in less than 2 years. 95% of the CO2 that has been injected into the subsurface has mineralized. So it's gone from then gas to fluid form, and then to solid mineral form in less than 2 years. And when it's solidified or in mineral form, then it's locked away permanently. The next time this will be open to be able to weather and release CO2 back into the atmosphere is assuming that there will be no volcanic eruption just underneath this plant. Then this will be when the surface of the Earth has eroded all the way down to this reservoir, this carbonate reservoir in the bedrock. And then we're probably talking millions of years. So in a human perspective, this is a permanent storage way of getting rid of the CO2, basically. So, and this is then, as a technique, is really interesting because they're using geological natural reactions that happens in nature, regardless if you pump it down, if you have a basaltic rock, like I can show you basically, like this one. If I put this one out into the rain, we will have the CO2 from the atmosphere will start slowly reacting with these rocks and then forming these minerals. So comparing these 2 years to the time that it will take if we pump this down underneath the ocean floor, which is the sandstones there are much less reactive. So the same reaction will probably take this model to take thousands of years. And during that time, it's important, obviously, to know that the CO2 that we are injecting down into the subsurface, that it stays down there. And this makes the Icelandic technique that they've developed here very interesting technologically. So then we move from Iceland to northern Sweden, and this is actually a little bit north of where I'm sitting today. So this is Kalix, which is about 1 hour north of here. And this is a paper mill. This is Karlsborg paper mill outside of Kalix. where they have then obviously, since it's a paper mill, they have CO2 emissions. So this is a point source. But what is the fun thing? This is a geological map of the area. And these different colors show different rock types in the bedrock. And these different rock types, they have formed through different geological processes, either deep down into the crust or on top of the crust or on the ocean floor and so on. But what is the fun thing here is basically that in the black circle here, that's the paper mill, the location of the paper mill. And what is this sort of pale greenish area is where we have basaltic rocks. So we have the exact same geological conditions as they do in the Carbfix site. So this laid a foundation for a project that we started a few years ago now, like 3 years ago. But with a big difference here, basically, is, and then I generalize a little bit, but I say that the Icelandic rocks, some of these rocks, they are formed, I mean, today, so they are extremely young. But let's put an average on the Icelandic rock at 2 million years. And then the Swedish equivalent basaltic rocks in this area would be 1,000 times older. So during these 2 billion years, a lot of things, geological processes have happened to Sweden. We have collided with continents, we have drifted apart, and all these processes have shifted or changed the chemistry of the bedrock of Sweden. It has deformed the bedrock to various degrees here. So we are in a different position compared to Iceland, even though we had the same starting point. These rocks were both formed as basaltic lava flows. So what is sort of the easy thing to see in these pictures of the rocks here is that in the Swedish basaltic rocks, we lack this porosity. We don't have this sort of sponge-like texture, the holes and pore spaces that we have in Iceland. So this is something that we're looking into right now. And in this project that we're doing now, we're looking at roughly 10 different sites in Sweden with the potential of assessing the reactivity of the basaltic rocks in these areas with carbon dioxide. And then just as a first assessment to look into the potential to use these as storage sites then. Then we have another project which connects to mine waste, basically, which is already crushed rock, which is then reactive also to carbon dioxide in different ways and different forms. And where we have sampled then 4 different mines in northern Sweden and Finland with the potential of looking into how much, if any, CO2 that can be sequestered into the mine waste on these different mine sites here. So this is what we're doing, and then our colleagues at the Geological Survey of Sweden, SGU, they are working with looking at offshore reservoirs. This is marine storage again, so they are looking at sandstone formation outside of Gotland, and this has been in the media just a couple of weeks ago. They have drilled through this sort of orange formation outside of Gotland, which is called the Faludden formation. They have drilled that now from sort of onshore in Gotland, and now they are doing geophysical assessment of these rocks with the potential of putting sort of a number on the storage capacity. How many million tons of CO2 can be potentially injected into these reservoirs? And then there is a small reservoirs also in the southern tip of Skåne, but I think that SGU is focusing these days on the Faludden formation off the coast of Gotland. And in the projects that we are doing from this university, we're then working together with Carbfix, since we are interested in the methodology and the technique that they're using. So we've also sampled the bedrock of Carbfix, so we use that as some sort of reference site, which we can then compare the reactivity and the efficiency of the Swedish bedrock in that sense, compared to Iceland, where we know that this technique works, even though it's small scale in Iceland. So what we're doing then, we are looking at 2 different themes when it comes to this. We're looking at reactivity, and we're looking at permeability. So reactivity, that's the mineralogy, the building blocks of these rock types and the chemistry. These are the minerals that will react with the CO2. And then for permeability or porosity, we are looking at what's sort of the fracturing network, how how much empty space or pore spaces are there in the subsurface? So how much can be injected of these then fluidized CO2 in this sense? And then we characterize these sites basically, or samples that we've taken, using a variety of different analytical techniques, both in 2D and 3D and so on. So then the question that we've basically gotten from day one in this project, then can we store, and how much can we store in the Swedish bedrock then? This is sort of the question of interest. And then being sort of halfway through the first project here, we can say as sort of a typically scientific answer, saying that, yeah, maybe, perhaps, probably, but we don't really know the efficiency yet. We have not yet tested the geological samples that we have together with the biochemical process engineers here, where we do an experiment and look at the efficiency of the reactions between our geological samples and CO2 in that sense. So, and then we don't know the capacity as well. This feeds back to the permeability, how many millions of tons of CO2 can be injected per year. So we can say from preliminary results, basically, that the mineralogy in a few of these sites looks favorable, but we cannot, at this point, put any numbers on anything. And then there is obviously the problem with the timeline. We don't have much time to develop these techniques here. And I will talk much more about this in the coming few slides then. So time is obviously an issue in the upscaling of any CDR or CCS technology in this sense. So I'm sort of interested, as a scientist, I'm interested in the limitations of things. I've done that in the past when I worked with ore geology. I want to understand what, in that case, the mining, what I cannot deliver. And when it comes to analytical techniques, what are the limitations? What can we not see with these techniques? And the same approach I've taken also with the CCS then. What are the limitations? What can we not expect from this technology? And then it's, to me then, super obviously that the storage capacity, the number of million tons per year, that's a huge bottleneck for this industry. An industry which is in sort of the starting blocks as it is now. But apart from the storage capacity, there are still unresolved other issues like finance. Who will pay the bill for this technology? There is yet no common policy framework for this. How should different societies and nations act around this? Then legislation. Obviously, today in Sweden, it's not allowed to store CO2 onshore. So there are legislative issues that then would need to be resolved if this is a working technology for Sweden as such, or for other countries. And then it's something that's called MRV, which is basically to measure, report, and to verify the amount of CO2 that is pumped into the subsurface, to know that after a long time that it actually stays down there. And to put numbers on these things, there need to be international agreements, international standards for these. And those standards do not exist as it is today. So there are a number of hurdles for this technology then to be able to upscale. And then connecting back to the timeline. A lot of problems to upscale, but we don't have much time to do this. And then if you're looking at what is being published these days around this, when it comes to storage capacity, this is basically just from the close vicinity to Sweden. These are numbers. Left-hand side, these are numbers from Norway. This is the Norwegian continental shelf, where it's estimated that 80 billion tons of CO2 can be stored. That's the equivalent of the European emissions for 23, 24 years, something like that. The huge number, 2,500 billion tons for over Iceland. These are the red areas in Iceland. These are the areas in Iceland which are better suited basically for this type of storage. And then 2,500 billion tons. It's a huge reservoirs, which would then equal over 60 years of global emissions that Iceland alone can store. But these are numbers that are only in theory. Nothing of this is basically verified as it is today. There is also in the same paper by Snøbjørnsdottir in 2020 they have a map showing basaltic rocks. This is the lower right-hand picture here. Basaltic rocks, which are then orange and purple in these areas, basically just to show that there are a lot of basaltic rocks around, but much of these areas obviously are not available. So storage capacity is a problem, even though in theory there are huge reservoirs for this. So then today, just last week, basically, there is an international think tank called the Global CCS Institute. They published their yearly report, and then stating that as today now, then there are over 40 CCS projects in operation and about 350 under development, different stages of development. But if we compare the 40 billion tons of CO2 that we emit to the atmosphere every year to what is being captured and stored, then what is being stored is 0.1% of what we emit in total. So 0.1%, that's nothing, basically. So then Global CCS Institute, since that's a think tank, this is an industry organization. Many of the members here are the oil companies. They tend to, in their report, to be a little bit more positive, maybe, towards the CCS project and the upscaling of things, but they still recognize that this will require a strong growth, and not just in Europe and the US, but around the globe then. And if we're looking at scientific publications of this, just to mention a couple, it's estimated that we might reach 10% of what is required when it comes to storage capacity by 2050. And then also publications saying that we will almost certainly not achieve this. This is too much. The progress is too slow when it comes to increasing the storage capacity. So basically, bottom line for this, there will never ever be a silver bullet of this. So CCS in consideration should be then only complementary to other means of sort of major cuts and reductions in the CO2 emissions, where CCS will be a piece of the puzzle and possibly just only a small piece of this puzzle. And then, I mean, just to throw in an extra thing, we talked about using bioenergy or biomass for energy and then connected to carbon capture and storage, starting out the presentation here. If we were to deploy this at large scale here, which then would be a negative emissions technology, the land area that would be needed to grow these bioenergy crops then to feed this system basically is anything between 1 and 8 million tons, 8 million square kilometers of land area here. And 1 million square kilometers, that's roughly the equal size of Sweden and Finland put together, where we will grow biocrops only in these two countries. 8 million square kilometers. That's roughly, not fully, but roughly the size of Europe. I mean, it speaks for itself that to fully deploy BECCS at this scale will never happen. I mean, to grow biocrops in an area this large, this will not happen. So to sort of cook things down a little bit and rounding off the talk, there is a lot of activity on the capturing side. There are a lot of companies now active on planning and slowly but surely starting to being more advanced and implementing capturing, which means that we will be able to capture a lot of CO2, but then we need to decide if we should then store it or what will happen with the CO2 then. So then it will become a question between storage and utilization. And utilization is using the CO2 then for different products here. So we will have sort of permanent storage against any kind of product, preferably a long-lived product like this, and not short-lived where we just sort of push the date of emissions like a week or a few months ahead. So this will be a question between CCS and CCU. And from the industry side, it's fairly clear that when they have captured the CO2, then it's a question for them, can they make money out of that? And if they can make a product out of the CO2, they can make money out of it. Then that is obviously of interest for the companies. And instead of then sending it off for permanent storage and paying someone else, to inject and store the CO2. So, I mean, all in all, sort of the take-home message, basically moving forward from this, would be to focus on reductions in the global emissions by other means, and having sort of CCS on the side, not relying that this will be able to scale to the levels that are needed, projected. We are needed, at worst case scenario, there is a need to store about 10 gigatons of CO2 by 2050. This is highly, highly unlikely that we will meet that. So considering CCS or CDR, carbon dioxide removals, as they will not work, even if they will be developed sort of on the side, but focus on reduction of the emissions by other means instead. That would be the first take-home message. So this is sort of a bit on the negative side, which is everything these days with climate change. So I figured I will throw in a different take-home message as well. And then I will quote Kevin Anderson, and he said and he's phrased this in a different ways over the past few years now, but he's saying that right now we are choosing to fail, where the keyword is choosing. We know what to do, we know how to do it, but we simply don't do it. So if this is where we are today, then for tomorrow, then let's then choose not to fail, which we owe our kids and their kids and their kids moving forward like this. Thank you. And now we open the floor for questions, I guess.
Thank you so much, Glenn, for an utterly brilliant talk. It was extremely pedagogic. Thank you so much for framing it in your motivations for doing this research, for doing this science, and your very chilling and realistic assessments. I'm going to switch off the recording, which means that everyone can put their they can